This is a question on bounds, and we've been given quite a complicated formula for the acceleration due to gravity g, 2L over t squared multiplied by sine x, x being in degrees. Experiment's been done, these are the results, and we've been asked to find the upper and lower bound of the value of g. Okay, t, l, and x have different degrees of accuracy. So let's form a table and sort out what are the upper and lower bounds of each of these variables. So I've drawn a table and we'll fill in the blanks, so to speak. Let's have a look at t. T has a value of 1.3 and it's correct to 1 decimal place. So even though 1.3 is quoted as the result could be from a range of values. The trick to use is to work out what the next value up would be. Well, the next value up will be 1.4 and the next value down will be 1.2. So the question is, what range of values would get sucked in such that the answer would be quoted as 1.3? Well, they would be at the halfway points between these resultant values. In other words, everything above 1.25 would be quoted as 1.3, and everything below 1.35 would be sucked in and quoted as 1.3. So this range of values between 1.25 and 1.35 all turn up as the result of 1.3. So these boundaries are in fact the lower and upper bounds of our variable t. This is the lower bound and this is the upper bound. So let's fill our results in. The next value up for t we found out to be 1.4, and the next value down 1.2. The upper bound is 1.35 and the lower bound is 1.25. Our variable L is quoted as 4.50, correct to 2 decimal places. So both these numbers are quotable. So what would be the next one up? Well, the next one up will be 4.51. And the next one down, 4.49. Again, the upper bound will be halfway between these two numbers, which will be 4.505. And the lower bound will be halfway between these two numbers, which is 4.495. Do you notice how the upper and lower bounds add an extra decimal place to the answer? So let's do the same for x. X is quoted to the nearest integer. So the next integer up is clearly 31 and the next one down is 29. So again, the upper bound will be halfway between. So this is 30.5 and the lower bound is 29.5. Well, that's done most of the hard work, but we've got one more important decision to make when finding the upper or lower bounds of g. Let's have a look at that. So for each of these variables, L, T, and X, we've got an upper and lower bound to choose from. The thing is, look, when we want g to be its greatest, in other words, the upper bound of g, the highest value of g, clearly, because L is in the numerator, we want L to be its equivalent highest value. But because both t and x are in the denominator, we would want t to be the smallest. This would give a higher result for g, and we also want x to be the smallest. So we would want the upper bound of L, but we would both want the lower bound of x and the lower bound of t. The rest is really just arithmetic. So I've written out both the upper and lower bounds of g using the numbers from our table up here. Right, calculating these two, we will get. So there are our two results for g, but we've asked to make this to 3 decimal places, means the cutoff will be here and here. So my two results are 11.710, that's to 3dp, and 9.719, and that's also to 3. And those are the two answers for part A. I probably should say that we were able to choose the lower bound of x in the denominator here because sine x will go down as x goes down, if you see what I mean. The value of sine of 30.5 degrees is greater than the sine of 29.5 degrees. So we were right to choose the lower bound of x because that would make sine x lower. Therefore, if we wanted the upper bound of g, the result for g would be greater. Let's have a look at part B. They've asked us to really consider our two values of g here. The value for g is at the mercy of the worst measured of our variables, because you can have super accurate results for L or X, for example, but if you have a poor measure of accuracy for t, the whole result will be dependent on that poor value. I suppose the crucial point here is that what degree of accuracy gives the same answer, because clearly we've got two answers here, 11.710 and 9.719. We've got to reduce the accuracy of our results until we get the same result. So let's try two significant figures. G upper bound, but two significant figures, only two figures are recognised, so these two are the only ones we're going to use. But because we've got a 7 here, we have to round up, so G would be 12. And the lower bound, G would be equal to two significant figures, 9.7. So there's still no agreement. Let's try one significant figure. With only one significant figure, G upper bound will be equal to 10. And the G lower bound would also be equal to 10. So at this point, the results agree. So a suitable degree of accuracy of our results can only be quoted to one significant figure, and that would be the answer.